Okay, so in our previous video, we end up with 4 different methods to find the change in enthalpy. And we said the last one is not for this course. You will learn about that in the next chemistry courses. But we're going to investigate the first 3. The first one, which is the most challenging one, is the calorimetry. And we're going to talk about 2 types of calorimeter, the bomb calorimeter and the coffee cup calorimeter. And we're going to learn about some basics about these, and then we're going to learn about the calculation, how to do the calculation with these calorimetry. So the first one, bomb calorimeter, is a constant volume calorimeter, and coffee cup calorimeter is a constant pressure calorimeter. So let's learn more about these things. So first of all, what is calorimetry? Well, calorimetry basically is the measurement of heat exchange to find the enthalpy. So you know that in constant pressure, we've learned it in the previous lectures that in constant pressure, Q is equal delta H, right? So if we can find the heat, we can find the enthalpy. And we also learned that Q of the system is exactly the same amount with different sign of Q of the surrounding, right? So in our case, we are investigating a reaction. So our system is a reaction. So therefore, Q of the reaction equals negative Q of the surrounding. So in order to find the Q of the reaction, we can easily find the Q of the surrounding. And the surrounding, we've already learned about calculating heat. So we can easily calculate the change in temperature of the surrounding. And if we know the change in the temperature of the surrounding, we can use the formula mc delta T. If we have the delta T, if we know the mass of the surrounding and the specific heat capacity of the surrounding, we can easily find the Q of the surrounding, and then we can find the Q of the reaction. So what happens in bomb calorimeter? So this is the schematic view of bomb calorimeter. Bomb calorimeter is constant volume calorimeter. So you see the reaction or the compound are trying to find the Q of that is in a closed container. The bomb calorimeter usually used for compounds containing carbon, hydrogen, and oxygen. From here with this pump, we put O2, excess O2, so to make sure that the product we get is CO2 and water. And the pressure is not constant, so it's moving, but the volume is constant. It has this thick wall container, it does not move, so the volume is constant. We have this wire going in to the container, and that can generate a spark, and that can start the reaction. Okay, when it starts the reaction, you're going to produce CO2 and H2O gas, and the reaction moves forward. It generates some heat. It is an exothermic reaction, and so that will be plus heat. So when this warms up, it's going to warm up the surrounding, which is the water in here, and we're going to monitor the temperature with the thermometer, and that will tell us the delta T. So we can calculate the delta T of the surrounding, and then we can find a delta H. So in bomb calorimeter, we have constant volume, not constant pressure, right? So how can we find delta H? Because we said Q in constant pressure, I write it as subscript P, in constant pressure is delta H. But in constant volume, it's not delta H. We know that delta E is Q plus W. And since it's in constant volume, work is 0, so this is 0. So basically what we are finding is the delta E of the reaction, right? So delta E of the reaction is Q in constant volume. Okay, so what we are doing in bomb calorimeter is finding the delta E of the reaction, but if you remember, we said that in most cases delta E exactly equal to delta H, or with some assumption it is almost the same as delta H. Okay, so if the work is 0, and it's since because it's in constant volume, if you remember, work was negative P delta V, and if delta V is 0 because volume is constant, then the whole work term is 0. So work is 0 and delta E is Q plus W. So W is 0, it's equal to the Q, and we find the E of delta E of the reaction, and we said in most cases with good assumption delta E equals to the delta H of the reaction. So how does the constant pressure calorimeter work? First of all, this kind of calorimeter is often used for aqueous solution. We have our styrofoam cup, coffee cup, that can isolate our solution. So we have the solution inside the coffee cup, and we cap the top part of that to prevent the loss of heat, and it is used to measure the temperature change of the solution. So since the reaction is in the solution, we check the temperature of the solution, and the solution is our surrounding, and the reaction itself is the system. So again, the same thing. So the Q of the reaction, which is our system, is negative Q of the surrounding. So we can find the Q of the surrounding with the same way as we did in the bomb calorimetry. So we have, if we have the mass of the solution, the C of the solution, we can measure the change in temperature with the thermometer here. So we can track the change of the temperature, and then we can easily find the Q of the surrounding, and that would be equal with a negative sign to the Q of the reaction. And it's in constant pressure, so the Q in constant pressure equals the delta H of the reaction. So one thing that you need to know is the difference between a specific heat capacity and heat capacity. So the term that we've learned so far was the specific heat capacity, and that was what we've used in MC delta T. So they write it as small c or capital C with sub s. Both of them are fine. So either lowercase c or uppercase c with subscript of s is a specific heat. So what is the difference with heat capacity? So let's first read the definition. The amount of heat in joule absorbed per unit mass of gram of the material when its temperature increases by 1 degree Celsius. That's specific heat capacity, and that's specific to each element, have a fixed number for that element. Okay. The heat capacity, on the other hand, is the amount of heat absorbed per quantity of an object. So it's not per unit of object, per some amount of mass of the object that increases the temperature by 1 degree Celsius. So the amount of energy for the unit mass of the object is a specific heat, and that's a fixed number you can Google or you can find from different sources for different elements. But heat capacity is not for a unit mass. So I have a cup, for example. I can tell you the specific heat is, I don't know, for example 2, and I would tell you that this cup weighs 10 gram. Okay, so we can multiply 10 gram because the specific heat is per a gram of that cup or anything. So since it's 10 gram, you multiply it by 10 to find the heat capacity of the cup. Okay, but when you are given heat capacity, it means whatever mass this item have, the heat capacity of the whole thing is this number. Okay, so when you are given heat capacity, it's you don't need to worry about the mass. So the mass is already inside the heat capacity, okay? And that's why you cannot find it in different sources, the heat capacity of items, because it's different. Is it like 10 gram of, for example, water? Is it 100 gram of water? How we cannot say that the heat capacity of water is whatever, but we can say the specific heat capacity of water is 4.184. It means that for 1 gram of water to increase 1 degree Celsius, we need this amount of energy. And that's specific for water, and that's why it's called specific heat capacity. But the heat capacity, it depends on the mass of water you have. So it might be 10 gram of water, it might be 100 gram of water, but that amount of water have this heat capacity. Okay, so we use this term. It's a little bit confusing. One thing that you can distinguish between specific heat capacity and heat capacity is the unit. So you know that the specific heat capacity have the unit joule per gram per degree Celsius, because it's per unit of gram. But for heat capacity, it's not per unit of gram, it's per degrees Celsius. It's for 1 degree Celsius for any amount of mass. Okay, so the unit for heat capacity is joule per degrees Celsius. So if you see the heat capacity with this unit, it's heat capacity. If you see this unit, it's specific heat capacity. And the difference is when you're calculating the heat, so you know Q equal MCAT, right? So you have this mass term, M term, because the specific heat tells you the energy required for 1 gram, so you need to multiply it by the mass that you have. But when you're using heat capacity, the Q, you don't need to put the mass because they already put the mass inside the heat capacity, so it's just C delta T. And this is usually used for calorimeters because the calorimeter might have different components. So we cannot say the styrofoam cup is this, the cardboard on the top have this specific heat capacity, the mass of styrofoam cup is this, the mass of this one. So it has different components, right? And that makes it very confusing to give you all of these details. Instead, they measure the amount of energy for this mass of calorimeter with all of its components. They measure that and say, okay, to increase the temperature for this whole calorimeter for 1 degree is this amount. Okay, so for calorimeter, usually what we have is heat capacity instead of specific heats. Okay, so usually for heat capacity, for calorimeters, we get heat capacity with C, and that's uppercase C. The specific heat capacity is lowercase c or uppercase C with sub s, as showing its specific heats. Okay, so we're going to practice more using these two probably on the worksheet. In this video, we have some practice with working in calorimeter in general. So let's do this problem together. So dissolving 6 grams of calcium chloride in 300 milliliters of water. Okay, so in total, how much solution do we have? So one thing you need to know that, and you have to note this, that the density of water is 1 gram per milliliter. So if you have 300 milliliter, you have 300 gram of water. Okay, the density of water is 1. Cause the temperature of the solution to increase 3.43. Okay, so you have your solution, it has an increase in temperature, so it gives you the delta T directly. With this amount, assuming the specific heat of solution is 4.18 joule per gram per degree Celsius. Again, one of the things that, however, it's directly mentioned is a specific heat, but we also can look at the unit. It's joule per gram per degree Celsius, so it's a specific heat. And assuming the calorimeter absorbs no significant amount of heat, okay, determine the delta H of the reaction. So we have this reaction going on in the calorimeter, so we are trying to find the delta H, okay. So before we start solving this question, tell me, so we know the system is the reaction, the surrounding is whatever surrounds the reaction. So what is the mass of the surrounding? So our surrounding is the solution that the reaction takes place in, and the mass of the solution is the mass of the solvent, the solute, which is the calcium chloride, and we have 6 grams of it, and the mass of the solvent, which is water, and we have 300 grams of it. So the mass of the surrounding is the sum of these two, and it's 306 gram solution, okay. Okay, so what do we have in the calorimeter? We know that the Q of the reaction equal to negative sign of Q of the surrounding. So let's look at this in a different way. So let me erase this. So all the heat exchange in the surrounding and the system equal to 0, right? That was the same thing I said. So if Q of the reaction plus Q of the surrounding equals 0, then Q of the reaction equal negative sign of Q of the surrounding. But we write this assuming something which is mentioned in the question. Assume the calorimeter absorbs no significant heat. So we didn't even write that, but I want you to know what that means. So let's write it, and since it's 0, we just cross that out, okay? So in a calorimeter question, you have to write down the heat that happens in a calorimeter, okay? Because the calorimeter itself is an object, right? So it's taking heat, it's absorbing heat or releasing heat, okay? So it has a Q itself. So you have to find that as a Q cal. And that's part of the surrounding, yes, but we have to know what that is, okay? So we know the Q of the reaction equal Q of the surrounding. But what is this surrounding? It's the Q of the calorimeter plus Q of the solution, right? So Q of the reaction plus Q cal, which is the heat of the calorimeter, plus Q of the solution, these are part of our surrounding, equals 0. The question says assume the calorimeter absorbs no significant heat. So the Q of the cal, the question says assume it's 0. So we have the Q of the solution to find the Q of the reaction. So Q of the reaction is equal to negative sign of Q of the solution, okay? So it's negative M of the solution, I just write SLN, C of the solution, and delta T of the solution, right? Q of the reaction equal negative, what is the mass of the solution is 306 gram times the specific heat of the solution, which is 4.18 gram, not gram, sorry, joule per gram per degree Celsius, and the delta T is 3.43 degrees Celsius. So that is, which is 4.39 times 10 to the 3 to the third joule or if you want to make it kilojoule, it's just moving 10 decimal place or 10 to the 3, so it's 4.39 kilojoule. Okay, so this is the amount of energy that is released for dissolving 6 gram of calcium chloride. So this is per 6 gram of calcium chloride. Okay, but we want the delta H. So if you remember the delta H in a thermochemical equation, this is a balanced thermochemical equation with a delta H, and we know that delta H for this equation is for 1 mole because the coefficient is 1, so it's per 1 mole of calcium chloride, not for 6 gram. So in order to find that delta H, we need 1 mole of calcium chloride, not 6 gram. Okay, so we can use this conversion factor, this per joule, or we can just do that the same thing with a kilojoule. So 4.39 kilojoule per 6 gram of calcium chloride, we can use that conversion factor to see how much energy released by 1 mole, and that would be our delta H. Okay, so 1 mole of calcium chloride, and we have to go to gram to use this conversion factor. So first we have to go to gram, so I don't want the mole of calcium chloride, I want the gram of calcium chloride, and you can use the molar mass. So 1 mole of calcium chloride is 110.98. Let me write this again. So it's 110.98 gram of calcium chloride, and I don't want the gram of calcium chloride, I want the kilojoule of calcium chloride of the reaction. So that's a gram of calcium chloride. So we have this conversion factor here. So we know that for 6 gram of calcium chloride we have 4.39 kilojoule. Okay, so therefore we can cancel out mole of calcium chloride with mole, gram with gram, and we end up with a kilojoule for 1 mole of calcium chloride, and that's actually our delta H, right? So that number is negative 81.2 kilojoule. So that is the delta H. So the delta H is negative 81.2 kilojoule. So the first part was not that hard. So we know that the Q of the reaction equal the Q of the surrounding, and our surrounding is the calorimeter and the solution. The Q of the calorimeter, the question says assume it's not significant, so we assume it's 0. So we just find the Q of the solution. The Q of the solution is MC delta T. We have all the components. We can easily find the Q of the reaction. The more confusing part is how to find the delta H when we have the Q of the reaction. Well, for delta H, we've learned in thermochemical equation that the delta H is equivalent to the coefficient in the balanced chemical equation, the number of moles of the coefficient to the energy. Okay, so since the coefficient for calcium chloride is 1, so the energy for 1 mole of calcium chloride is the delta H, not 6 gram. The question says 6 gram. So you have to solve that for 1 mole of calcium chloride, and that would be your delta H. So this example is not specifically calorimeter, but it basically uses all the concepts that we have in a calorimeter. Okay, so we are burning the methane with this equation, right? And it produces heat, and this is the enthalpy, that's the heat that is produced by this reaction. We are burning the methane, and it asks us to find the amount of heat required well, not the amount of heat. It's basically asking how many moles of methane it is required to increase the temperature of water. How much water? 200 milliliter, and we know the density is 1, so that's basically 200 gram of water, right? Increasing from 20 degrees to 100 degrees Celsius is the boiling point. But we have to assume that only 50% of the heat generated goes to the water. So the methane is burning, it's producing some heat. That's the Q of the reaction. 50% of the Q of the reaction goes to the water. 50% of the Q goes to something else, the surrounding. Okay. And how much methane is needed to increase that amount of water from 20 degrees Celsius to 100 degrees Celsius. Okay, so it uses the same concept. Okay, so the Q of the reaction, which is that reaction, plus the Q of water plus the Q of the surrounding. Well, water could be the surrounding, so let's say instead of surrounding, let's say everything else. Everything, I'm going to write everything else, okay, equals 0. So that's the amount of heat exchange, okay? Some heat produced with the reaction, some of it, or 50% of it goes to the water, 50% of it goes to everything else, okay? So I can say that Q of the reaction equal to the negative of Q of water, H2O, plus Q of everything else. I just write everything else, okay? Or let's write the else, make more sense. So so the sum of these two with a negative sign should be equal to the Q of the reaction, but 50% of it, or let's say half of it, so half of the Q of the reaction goes to the water and half of the Q of the reaction goes to everything else, okay? So I can say half of Q of the reaction divided by 2. Half of that equal the negative sign of Q of H2O, right? I can say that because the question says 50% of it. So half of the Q of the reaction equal the negative sign of Q of water, okay? So if I multiply this by 2, then that will be Q of, so 2 with 2, and then I have 2 here. So Q of the reaction equal negative 2 Q of H2O, right? So then for Q of the H2O, I can write MC delta T, right? So negative 2 times the mass of water, which is 200 milliliter, and that's 200 gram. So 200 gram of water times the C of the water is right here. So 4.184 joule per gram per degree Celsius times the delta T. What is the delta T? So it's going from 200 to, sorry, it's going from 20 to 200. So 100 final minus initial minus 2, 20, and that's degrees Celsius, okay? So the answer to that is, let me write this here. So the answer to that is negative 1.34 times 10 to 5 joule, okay? Or I can say a negative 134 kilojoule, okay? So that's the amount of energy required to increase the temperature of 200 milliliter water from 20 to 100 degrees. So that's the energy I need, okay, to do that. But the question is not asking for the energy, it's asking how many moles, okay? How many moles? So I need this amount of energy, 134 kilojoule. I want the moles, so remember about thermochemical equation. So we can relate the energy to the mole, right? So this is a balanced thermochemical equation, and this is 1. So for 1 mole, we have this amount of energy. So I can use that as a conversion factor. So I don't want the energy, I want the mole of methane, CH4. So for negative 890.4 kilojoule, 1 mole of methane is needed. So I can cancel out the kilojoule with kilojoule, and I end up with a mole of methane, and that is 0.150 mole of methane. Okay, so this is the most challenging part of this, I would say, this whole course. Okay, the last chapter is the most challenging part, and heat calculation and calorimetry is more challenging, so we're going to have more practice on this. But the thing that you have to know is just knowing the basics, knowing that what's going on in that reaction, knowing the basics, and you can set up your equation. When you set up the equation, the rest is just playing with numbers, and that's math. Okay, so just go over this question again. So we have some water, 200 milliliter of water. We want to increase the temperature from 20 to 100, and that needs some heat. We require this heat from a reaction which is burning the combustion of methane, that we have the equation here. So we have the delta H of that reaction, so which means that 1 mole of methane gives off this amount of energy, and we know that 50% of it goes to the water. So we have to find how much energy required to increase that for the reaction to increase that temperature, and then we can use the thermochemical equation to find how many moles of methane is needed.